Good morning. My name is Angelica Cortes, and I am from the University of Puerto Rico, Maya West Campus. My major is chemical engineering, and this summer I have been part of the SROP program at the University of Michigan, working at the Department of Nuclear Engineering and Radiological Sciences, under the mentorship of Dr. Gary Wass. This summer I have been studying the diffusion of fission products in silicon carbide for the very high temperature reactor. The very high temperature reactor is a generation 4 reactor which is cost effective, it is safer in operation, and it is more efficient because it is able to reach higher temperatures. The particles that make the fuel for this reactor are called triso particles. Triso stands for tri-structural isotropic because the fuel particles are composed of a fuel kernel of uranium, and it is surrounded by 3 layers of isotropic materials, which are the inner pyrolytic carbon layer, a silicon carbide layer that follows, and the outer pyrolytic carbon layer. The silicon carbide is supposed to act as the containment of the fission products and a pressure vessel. For this experiment, we have been simulating the layer arrangement of these fuel particles. We have a 1 centimeter square silicon carbide substrate made by the company Raman Haas that is going to serve as our main layer. Then on top of that, we're going to deposit a layer of pyrolytic carbon by the means of chemical vapor deposition. This layer is meant to have a specific thickness that we could measure using Rutherford backscattering spectrometry, that it is performed using a particle accelerator, the Tandotron accelerator of 1.5 megavolts. Then we are able to implant the fission product that we desire on top of that pyrolytic carbon layer. We could either implant cesium or silver. Once the implant has been carried out, we can carry out again RBS to make sure that the implant was indeed performed. Once we implant this fission product, then we put a molybdenum cap on top of that using IBAD, which stands for ion beam assisted deposition. This molybdenum layer allows the fission product to not go into the surface because we want it to diffuse inside the silicon carbide. So this acts as a layer that prevents the volatilization of our fission product. Then Rutherford backscattering spectrometry follows again to characterize our sample. Then what proceeds is annealing of our samples at different times, which have been 10 hours and 60 hours. And all of this is carried at 1600 degrees Celsius, which are the temperatures that our reactor is going to use in real life. Once we anneal these samples, we perform RBS again to profile the distribution of our fission products inside the silicon carbide layers. So far, we have been able to analyze the silver fission product on top of the silicon carbide, and we have seen that at 10 hours and at 60-hour annealings, the distribution of the depth of our fission product in the sample is a Gaussian one. And we have also seen that since our preliminary samples didn't have the molybdenum cap, there was significant loss of fission product to the surface, and we want to prevent that. We also obtained a preliminary value for the diffusion coefficient of silver in silicon carbide, and this value was in the order of 10 to the minus 22 meters squared per second. And we have seen that this value is significantly smaller to the one seen at the literature. So our future work consists of improving the solution of the diffusion equation and be able to solve it with better boundary conditions. And we also want to anneal more cesium samples in order to obtain more data points for our purpose. And we also want to obtain a more consistent pyrolytic carbon layer for our samples. Well, thank you very much.